Hi everyone, welcome to the afternoon session. Our first speaker is Tony Feng from UC Berkeley. He has an interesting title, Structure in the Search for Structure. Let's welcome.
Great. So thank you very much for the invitation to speak and introduction. So I feel I have some explaining to do. This conference was definitely the most rigorously organized conference that I've been to, and other delinquent speakers would know that at a certain point you start receiving an email every 24 hours saying, "Urgent, please upload your lecture information." And so after getting enough of these, I decided, why don't I just upload an extremely vague title that can mean anything, that could cover any possibility that I would talk about. So that's how we ended up looking at this interesting title here. Okay, so the basic analogy which I want to pitch in this talk is that there is an analogy between number systems and geometric shapes. And especially this analogy, prime numbers are analogous to knots. So I think probably everyone knows what prime numbers are. On the left, we have some examples of prime knots. So knots are circles embedded into three-dimensional manifolds. Okay, so I was asked to prepare a talk for a general audience, and now I sort of suspect that maybe the audience I imagined was a bit more general than the one I'm seeing. So I prepared a warm-up example about what are primes? Okay. So I think we first encounter primes, most of us, in the concept of prime factorization. We learned that every positive integer factors uniquely into product of primes. I don't know if you ever asked yourself these questions, but I think it's natural to ask about the statistical structure of this process. For example, given a random n-digit integer, what's the probability that it's going to be prime? And if it's not prime, what's the probability that it has 2 prime factors or 3 prime factors or k prime factors for your favorite k? And in a similar spirit, but slightly different, what's the probability that it has a super long prime factor that accounts for at least half of the digits? Okay, so the first question here was addressed by something called the prime number theorem. The second question, as far as I can tell, was studied by Landau, the third by Dickman. But going through the answers, what I want to show you is that there's kind of analogous questions for knots. And to start framing this, we have to decide what's the analog of picking a random integer. And I claim it's the following construction. So let's take n strands of string, lay them down side by side, and then just start tangling the endpoints together. And then at the end, we'll tie them back. And we're going to call this resulting shape a tangle. So for example, if n is 2, then there's kind of 2 possibilities for what I might produce. I could either do nothing and get 2 disjoint knots, or I could end up with this one long knot. If n is 4, then there's a bunch of possibilities of which I'm displaying 3 different ones. And so you can kind of imagine how this goes. And so this is what I claim is the analog of a random integer. And what's the analog of prime factorization? Well, let's just observe that a tangle will decompose into a union of knots. So in this example here, we actually end up with 2 disjoint knots shaded in different colors, one red, one black. And each individual knot here is the union of some number of strands. So that's some measure of the complexity of the knot, which is going to end up being analogous to the complexity of a prime. Okay, so with this in place, we can start asking questions like, given a random tangle and n strands, what's the probability that at the end you're just going to wind up with one long knot? Or what's the probability that it has 2 knots or 3 knots or k knots for your favorite k? What's the probability that you end up with a very long knot that occupies at least half of the strands? So notice that these questions are linguistically similar to the questions I had on the first slide. And the claim is that they're also mathematically similar. So claim, the factorization of numbers into primes behaves like the decomposition of these tangles into knots. And this is actually something which I learned about in a YouTube video by Venkatesh. And since this is the age of data science, I've pulled for you some data from that video, the results of this little inquiry for random 100-digit integers. And I have to say, I don't know how he computed this, because when I was on the plane here, I wrote a program to try and replicate these numbers, and I just couldn't get my prime factorization algorithm to work quickly enough on 100 integers. I didn't try that hard, but at least I was able to replicate the data for the analogous problem of tangles. So here's the result of a Python script that runs a Monte Carlo simulation with 1 million trials on 200 tangles. And why is this 230 appearing? Because it's about 100 times the natural logarithm of 10. Indeed, if you think about it, you realize like the scale, there's a scale artifact in the prime numbers where, why do we work with base 10 numbers? So we're going to normalize it by the natural log of 10. That basically by design makes these first columns line up. But after we do that, we see that all the columns look pretty close. So the probability of 2 prime factors on a random high-digit integer is 2.5%. In the simulation, we get 2.6% for the knots. The probability of super long prime factors, 69%, and we get 70 for the super long knot. And so there appears to be some kind of resemblance here. And it's a theoretical result that if this 100 were to go to infinity, the columns would align more and more. Okay, so this was meant to be just a little warm-up example to ease into analogy again that number systems are like like shapes and primes are like knots. And like I said, knots are embedded in 3-dimensional space. So adding on a bit more to this analogy, the prime numbers embedded in terms of algebraic geometry and spectrum of the integers is like circles embedded in the 3-sphere. So I'm saying the integers are like the 3-sphere. Now, my college roommate was a biologist who studied zebrafish. So I don't know if anybody knows. Here's a zebrafish here. And why is this picture on the screen? Because, well, I asked, like, why would you study zebrafish? And he explained that, okay, these things definitely look very different, but in fact, the zebrafish shares a very large percentage of its genetic makeup with humans. Okay, so although, yeah, they don't appear similar, there is some structure which is extremely similar. And my basic point is that that's the kind of theme which we see also in math, that we have these different mathematical objects, they look very different, but if you know how to look, then you begin to see that they can be extremely similar as well. And just as DNA helps us articulate in what sense different looking organisms are actually similar, one way to articulate why different geometric objects or mathematical objects are similar is through things such as algebraic topology. So one way to articulate the similarity, for example, between primes and knots, is to look at the invariance that algebraic topology assigns to them. For a circle, you have homotopy groups, pi I. They're trivial in degree 1, and in degree 1, they're free on 1 generator. And for the spectrum of FP, the homotopy groups are 0 except in degree 1, and in degree 1, they're profinitely free on 1 generator. And this looks as close as you can get because these algebraic geometric homotopy groups are profinite by design. Okay, so let's take a little stroll through another example. So sorry, 3-sphere? Yeah, so that also has an explanation in these terms. It has to do with the triviality of the pi 1 and pi 2 spec set if you appropriately insert the infinite place. Yeah, so I didn't have on the screen to do the algebraic topology for spec set, but it is in fact similar. And so here's the kind of another kind of interesting parallel. So when you have 2 knots, K and L in the 3-sphere, then there's this notion of linking number, which tries to measure how many times one knot winds around the other. So in our example here, like we have two pairs of knots, and the first you have a linking number of 2, and in the second one you have a linking number of 3. And now claim that there's also a notion of linking number for primes, and I'll tell you what it is, mod 2. So mod 2, roughly speaking, we have 2 primes P and Q, and the linking number should be measuring whether one is a square mod the other. So more precisely, at least if primes are odd, then the linking number between P and Q will be 0 mod 2 if P times a certain sign is a square mod Q, and it's non-trivial mod 2 otherwise. Okay, so this sign depends on whether P is 1 mod 4. It starts to get a little technical, but the idea is it's measuring whether P is a square mod Q. Now, why are these guys analogous? I'm just going to sketch briefly in words, but one way to compute the linking number is to take this knot K, right? It's in the 3-sphere, and then delete it. And then what remains is the thing called the knot complement, and its fundamental group is Z. And its fundamental group is generated by the class of this little red meridian around the thing you deleted. And then the linking number is projection of this knot L to the fundamental group. That's what multiple of the red meridian get. Okay, so in other words, mod 2, the linking number is you take the unique double cover of the knot complement and you look at the image of this other knot inside that covering group. And if you study algebraic number theory, you know exactly how to turn those words into their analogous versions for the spectrum of the integers. Take Z, you invert P, there's a unique double cover obtained by joining the square root of this -1 to epsilon, and you look at the class of the Frobenius in that covering group, and that tells you that that's interpreted by whether or not the thing is a square. So that's why these things are analogous. And an interesting parallel here is that, well, the linking number is a symmetric quantity. The linking number of K and L is the same as the linking number of L and K. And in particular, it's symmetric mod 2. And it turns out the same is true for the linking number of knots. P is a square mod Q, Q is a square mod P, with signs asserted at appropriate places. And that's called the law of quadratic reciprocity. It's like one of Gauss's crowning achievements. And it's the beginning of the subject called class field theory, which is the beginning of Langland's duality. So what I'm getting at here is that these kind of like maybe relatively elementary geometric statements start to have these very deep arithmetic parallels. Okay, any questions? Oh, okay, that's a good question. So the question was, what knot is analogous to a prime number 2? And actually, the analogy doesn't really work at that level of precision. It's not like individual knots are analogous to individual primes. Just the kind of the structure of the theory is similar. Yes. So I mean, I guess okay. The question was like, can one be more? Can one look at these analogies in higher resolution, where not only do you look at the decomposition of into knots, but also the linkings and the So yeah, I think that well, linking numbers have an analogy, and the decomposition has an analogy that the analogy doesn't always pass through such refined questions. But it's a good question. Okay, so so let's circle back to this metaphor. I mean, I already told you about the zebrafish, but now I'm just going to give you a slightly more my own personal take on this kind of stuff. So I always think in terms of like cats and lions, because these are, well, a little bit closer to my experience, and they're kind of like creatures which you would at first glance never think of as being like the same thing or related. Right? Like if you were to encounter one of these in your home, it'd be different than if you were to encounter the other. But when you look at these things from the right perspective, from the right point of view, and catch them in the right moment, then you start to see there's also some uncanny similarity. And that starts to prompt you to look for structure, like a common structure which can explain these kinds of relations. And in turn, once you identify what that structure is, you can start using it and trying to find out more stuff. So what we're going to do is the analog of this in math, where we are going to now move on from this analogies that we know and try to generate new mathematics. By the way, so in addition to the title slide, which I mentioned was like deliberately vague to be able to fit any possible talk, this is also a slide which I would probably have included in any possible talk I give there. So although when one writes grant applications in number theory, you learn to always say that it's about the study of integer solutions to equations. Really, for me, it's always secretly about cats and lions. Or in other words, the kind of hidden similarities between seemingly different number systems. Okay, so like I said, first, just some attributions. If you want to learn more about the analogy between knots and primes, you can consult the book of Morishita. Or if you want to see more pictures of cats and lions, you can. I'm getting mine from this book here by Iwaku. Okay, so like I said, our next theme is how to generate more mathematics from this analogy. And a powerful way to do this is through a kind of actually trifecta, which was emphasized by Weil. We now call it vase Rosetta Stone. And well, for example, sometimes I guess like why 3? Like why is the integers like 3 minus why? Where did number 3 come from? And there's a possible answer here in terms of kind of third aspect of this system of analogies, which is kind of closer to both sides. So for example, you're going to have to believe me that the curve over a finite field is analogous to the integers. They're both curves in the sense of algebraic geometry of finite residue field. Anyway, let's suppose we believe that. Then there is a process to read off from geometry what the analogous topological object is. So let me just sort of walk through this briefly. So if a variety X for a finite field Fp, right? X is over spec Fp, and you should imagine that as a fibration. So it's like a topological space fibered over the circle, because we discussed circles are like prime numbers, spec Fp. And who are the fibers? So the fiber should be thought of as X, but over Fp bar. And then there's this principle in algebraic geometry, the thing over an algebraically closed field is like a thing over any other algebraically closed field. And so X over Fp bar should be like X over the complex numbers. And hey, if X is a curve, for example, then take the complex points, you're going to get a Riemann surface. So it's a two-dimensional manifold. So in the end, if X is a curve, you're going to get this analogous topological space, which is a fibration over a one-dimensional circle with fiber 2 real dimensions. And that's where this 1 + 2 = 3 comes from. Now, having said this, I'm going to sort of immediately caution that depending on what problem and what topological invariant you're studying, you may have to adjust this number 3, like maybe to 2. Okay, so let me give you some examples. So using this Rosetta Stone, problems in one context can have interesting parallels in other contexts. You can translate between these different mathematical contexts. And so here's an example. There's this thing called the Riemann hypothesis, and that's a problem about prime numbers and integers. So that occupies our arithmetic column. But as we know, there's spec Z is analogous to a curve over Fp. And in this case, we're going to make it analogous to a Riemann surface, H mod gamma, hyperbolic Riemann surface. And now there's this thing called the Riemann zeta function, but it's analogous to something called the zeta function of a curve in the sense of Serre, which is analogous to something called the Selberg zeta function of a Riemann surface. And you have the Riemann hypothesis, which is a question about the location of the zeros of the Riemann zeta function. You can formulate the analogous question for curves, and that's called Bayes' conjecture, at least more generally, when curve is replaced by an arbitrary smooth projective thing. And you can ask this kind of question in topology as well. And the answer is, I think, kind of understood. It's not always true, the analog of the Riemann hypothesis holds, but it's a question which has been studied. And I would remark that Bayes' conjecture, well, for curves, was proved by Bay, but in general was proved by Galeen, and the proof uses many ideas from topology. And of course, the Riemann hypothesis itself is still open. Okay, we can keep going. So let's look at the next problem on the problem set. So there's this thing called the Burchard-Swinerton-Dyer conjecture. And again, we're going to make something in each of these columns. So it's the kind of underlying geometric space will be sort of one dimension up from before. So we'll have a curve over spec Z or a surface over a finite field. And now we're going to get a 5 manifold M in this last column. Number 5 is 1 plus 4, because we're imagining our manifold as fibered over the circle with this complex surface fibers, so 4-dimensional real fibers. And okay, in the conjecture, there's the L function of the Jacobian of the curve. So that's our abelian variety is the Jacobian. Or we have the zeta function of the surface. And the conjecture is about the relation between values of this L function or zeta function and the size of a certain group. So it's either the Tate-Schaff-Raypich group of the Jacobian or the Brauer group of the surface. And the topological analog of that is something called the topological Brauer group. It's the torsion in the second homology. Okay, so it doesn't matter whether or not you know like what definitions of these objects are. I'm just trying to illustrate that there's this analogy, and this Rosetta Stone really it's quite precise in a lot of these cases where you can just write down a dictionary defining objects. And now here, whatever the BSD conjecture says, it has a complete analog in this middle column in geometry called the Arden-Tate conjecture. That's the point is to introduce that conjecture. And unlike the relationship between Riemann hypothesis and Bayes conjecture, here's a situation where both columns are completely open. So the archetype conjecture is known to be equivalent to the BSD conjecture positive characteristic, but basically no more is known about that than any other BSD conjecture setting. So still wide open in both columns. Okay, so we've seen here some ways to take this set of analogies, make them precise in this Rosetta Stone, and like generate more math from math that we have already encountered. I am not planning to. So actually, in this column, I don't really know what to put. And here, I don't know how to attribute, although it's a question that's studied. Yeah. Sorry? Not that I know of here. I don't know how to make the kind of analogous thing. But, okay, we're going to see in 1 second that one maybe not this conjecture, but other conjectures, one can formulate expectations or guesses or something. So the setup for that, okay, we discussed linking numbers of knots, right? One-dimensional things and three-dimensional ambient things. Now, more generally, if you have an odd-dimensional manifold, then there is a Q mod Z valued linking form on the torsion and its nth homology. So, okay, maybe I shouldn't say more generally. Let's say this thing exists and is kind of similar in spirit to a linking number. And on an even dimensional manifold, maybe it's more familiar where you know on the middle dimensional homology, there's an intersection form, so that's a self-duality you can attach to an even dimensional manifold. On an odd dimensional manifold, this is the natural thing, because there's no middle homology. So you take the middle, you round it down, take the torsion, that carries some kind of self-duality. And let me try to briefly indicate it geometrically. So we're going to have to imagine this red and blue things are n-dimensional inside 2n plus 1 dimensional space. Because they're torsion, if we multiply one of them, let's say the blue one, by its order, just say it's like 12, multiply blue by 12, then it bounds n plus 1 manifold, or n plus 1 cycle, let's say. Now with this n plus 1 cycle and an n cycle, you can intersect them inside 2n plus 1 dimensional space, you get an integer. But then you need to divide out by that thing you multiplied by earlier. We called it 12. So, okay, actually you get a rational number after doing this division. And actually it's not well defined because it depended on a choice of bounding n plus 1 fold. So it's well defined mod Z. So that's what this means geometrically. Now, for the more algebraically minded people, let me just now sketch how you construct this algebraically. So you observe that the torsion in H lower n is the torsion in H upper n plus 1. And that receives a surjection from Hn with coefficients in Q mod Z. And so if you had two things in this middle group, you could lift one of them to here. Okay, so you have one thing in each of these components, and you multiply them together, you get something in H2n plus 1, coefficients in Q mod Z, and then if you have Poincare duality, then that's Q mod Z. And Poincare duality will tell you that this is a non-degenerate pairing. Okay, so that's what algebraically, that's what our thing is doing. Okay, so I introduced this in order to tell you about conjecture. I'm calling this Tate's simplicity conjecture. Now, I didn't really think this, I thought I made up this word simplicity, but then I Googled it and it did seem to be in the dictionary. So, okay, anyway, let me tell you what the conjecture says. So, first of all, there's this table of analogies we discussed before, 3 columns, arithmetic, geometry, and topology, and 3 rows. And the rows are going to have a space, a group, and a pairing. The space will be a curve over the integers, or a surface, or a finite field, or a 5-manifold M. The group will be the Favourite group of the Jacobian of the curve, or the Brouwer group, which is H2, étal of the surface with coefficients in GM, or this torsion in H in second homology of the 5-manifold. And then there's a pairing on each of these groups. So the linking form is the topological one, which I just had on the previous slide. Maybe that's the most concrete to visualize. And then the other ones, you're just going to have to imagine analogy. So you either have something called the Castle state pairing on the Tate-Favourite group, or you have something called the Arden Tate pairing on the Brouwer group. And here, I'm lying slightly. So really the thing that Art and Tate constructed was on the prime to P part of the Brouwer group, where this is the same P as this. And then Milne came in later and found it on the P part. So more about that later. But let's just imagine, there is a pairing. At the end of the day, there is a pairing on this thing. Okay, and the conjecture is that the pairing is symplectic. So one can find this in Seminor Bourbaki of Tate, 1966. He conjectures that this Art and Tate pairing is symplectic. Again, really, he conjectures it for the prime to P part. They didn't have the P part, but more on that later. So first of all, I just want to clarify, what does conjecture mean? Because there's a kind of a subtlety here. So let's recall skew symmetric. Pairing is skew symmetric if for all u and u prime, u paired with u prime plus u prime paired with u is 0. Now, why is that different from symplectic? So symplectic means for all u paired with u will be 0. Aren't these the same thing? Well, not quite. So the second thing always implies the first. And in the absence of two torsion, it is equivalent. But if there's two torsion, it's not necessarily equivalent. And the second thing, as I say, is stronger. And at first glance, it's a somewhat interesting conjecture because like the topological analog is actually false. So you find 5 manifolds for which the linking form is not necessarily symplectic. For example, there's a thing called the Wu 5 manifold. So you might ask, like, why make this conjecture? Yes, that's true. So there's a subtlety here, which we'll revisit later, but it is non-degenerate on something called the non-divisible quotient, which conjecturally is the same thing as the whole thing. But yes, you're right. There's some non-degeneracy, which I'm surprised. It's a bit technical to discuss, but I'll circle back to that. Okay, so as I was saying, the topological analog is false. So like, why would you even believe in this? Well, Tate did have a good reason, which is, okay, he was more, oops, I should have called this geometry, but he was more focused on this part of the analogy table. And he said, well, okay, the Cassels-Tate pairing is symplectic. So by analogy, I'm going to just conjecture that Art and Tate pairing is symplectic. And here you have the original source text. He says this. He says Cassels for dimension 1 and I in general constructed this canonical pairing between the Tate-Fravich group and its dual of the dual abelian variety. Non-degenerate, the thing is finite, and alternating or symplectic. If the Tate-Fravich group of it can be identified with the original, for example, if you have a principal polarization identifying the abelian variety with its dual. In particular, Jacobians always have a canonical principal polarization. So for Jacobians, it says, hence in this latter case, and in particular, if A is a Jacobian, the size of this group should be a square. And here in the last sentence, he's referring to this kind of like algebra exercise that if you have a symplectic form on a finite abelian group, then the size will be a perfect square. Like if you have symplectic vector space, its dimension will be even. Okay, so that seems compelling enough, and this kind of was like a folklore knowledge in the community for many years until, somewhat shockingly, in the late 90s, Poonen and Stoll exhibited a curve whose Tate-Fravich group of the Jacobian had size not equal to a perfect square. Which means, how can this be? Well, it's just not really true what you see here on the screen. So Tate did prove that the pairing would be symplectic under some situation, but it's not quite the situation that he's referring to here. So in the small gap between what he actually proved and Jacobians, there are some counterexamples lurking. So in fact, okay, so what he proved is if you have a polarization which comes from a rational divisor, like the divisor rational of the ground field, then it will be symplectic. And Jacobians have a canonical principal polarization, but the divisor may not be canonical. That's the issue. And so that's the kind of technical gap. So that seems to put our conjecture on somewhat, let's go back to this conjecture. It seems to put it on somewhat shaky footing where both the analogous versions are in fact false. So let me discuss a little bit the history of this conjecture. So before I start into that, actually, I want to set down some terminology. So let's write Brouwer of S sub ND. for the maximal non-divisible quotient, meaning take this Brauer group and quotient by all of the divisible stuff. Okay, why do I do this? Well, in fact, conjecturally, the Brauer group is finite. And so it only has 0 as its only divisible element, so you're doing nothing. The Brauer sub nd is the same as Brauer, conjecturally, but that's a big conjecture. That's equivalent to the Arden-Tate conjecture. And so this Brauer sub nd is just some way to talk unconditionally about what the size of the group should be. It's like an unconditional finite group. And conjecturally, it is the same as the Brauer. Okay, so write that down. This Brauer sub nd is finite, and it should be equal to the Brauer group. But that is equivalent to the Arden-Tate conjecture, as we know now by results of Arden-Tate and Mill. Okay, so really, going back to Sam's comment, really the skew symmetric form is defined to be non-degenerate on this quotient, which should be the same as the whole thing, but really it's on this quotient and you inflate it to the whole thing. So the conjecture implies that the size of this thing, again, it should be the same as the size of the Brauer group, is a perfect square, because it carries the non-degenerate symplectic form. Well, okay, so actually in 74, Manin wrote down an example of a surface where the size was 2. And 2 isn't a perfect square. So, okay, but contrapositive, then the conjecture is, of course, false. Actually, this conjecture is basically the only thing I want to talk about. So, there, I guess my job is done. There's no applause. So I've got to keep going then. So, well, it was done in 1974, but then later it became undone because in 1996, Urabe found mistakes in this counterexample. And moreover, Urabe proved that the size will always be a perfect square, at least if p is not 2. Okay, so not only the counterexample was, this particular counterexample was wrong, there is no counterexample of this nature anyway. And then later in 2005, in a paper with almost the same name and almost the same journal, the Liu, Lorenzini, and Raynaud showed that if you assume the size of the Brauer group is finite, then its size will be a perfect square, even in characteristic 2. So one is getting a bit more in characteristic 2, but I mean, one really has to make this assumption. You don't get any unconditional result. You don't get any unconditional result about this finite quotient. You really have to assume this, and you assume by some chain of theorems, you assume the BSD conjecture, you compare the size of the Brauer group to the size of some Tate-Charevich group, and you show that things work out to be a square. Okay. Any questions? No. So what he does, he proves some kind of like restriction of it to co-isotropic spaces, symplectic, and then by like some, well, just by some elementary thing, then you can get the whole thing as a square. But no, he doesn't prove the thing is symplectic, actually, and I want to emphasize that. Yeah, he does not actually prove that the original conjecture that the pairing is symplectic. Okay, so I think it's useful to organize these results according to the following dichotomy. In number theory, there's always 2 primes, P and L. And P is the characteristic of the geometry, which means like your schemes will be over F, in characteristic P. Or characteristic P could be zeros, they could be in characteristic 0. L is the characteristic of the coefficients of cohomology. So you're taking like L adding cohomology. And the general principle is that the situation is very different if you consider L not equal to P or L equal to P. It's very different. The kinds of analogies I gave before are really for L not equal to P. So L not equals P behaves like singular cohomology of topological spaces. When L is P, that behaves weirdly and wildly in many ways. And a simple example is like if you take the affine line over FP bar, so I said that's analogous to the affine line over the complex numbers, which is complex numbers, contractible. So the cohomology is 0 if you take L-adic coefficients where L is not P. But if you take coefficients in FP, then things it's not 0, it's actually infinite dimensional. So it's kind of like crazy. So this is a serious breakdown of the analogy of topology. And when we're talking about Tate's simplexity conjecture and between geosymmetric and simplex, really we're caring about L equals 2. All the content is at L equals 2. So L is 2. So in Arabe's result, he analyzes the 2 part, but he has to assume P is not 2 for this reason that he doesn't want P to be equal to L. And for Liu, Lorenzini, and Raynaud, they are able to handle the 2 part even in characteristic 2, but of course they make a strong assumption. They assume the Artin-Tate conjecture, or in other words, they assume the Swinnerton-Dyer conjecture over finite fields. Okay, so now I'm going to kind of come back to talk about the question about the symplectic form. And I'm going to first do that in the case where L is not equal to P. In that case, first of all, let's recall that I had defined the linking form, came from Poincare duality. It came from this pairing between H upper 3 torsion and H2 coefficients in Q mod Z. And I didn't tell you what the Artin-Tate pairing is, but at least when L is not equal to P, it's something which is extremely analogous. Okay, so again, you have Poincare duality, you have 5-dimensional duality. You just have to stick the subscript L everywhere. So you have H3 with coefficients in ZL torsion, and that turns out to be the L power torsion in the Brouwer group. And then you have H2. If you have 2 things in this group here, you lift one of them to here, you multiply them together, and up here, and then by Poincare duality, that's that. And so the pairing, the algebraic definition of the pairing carries over completely to this geometry over a finite field setting. Now, there's one other difference between these 2 lines, which is like these funny 1s and 2s floating around. But that refers to a Tate twist. So that's like some kind of twisting of the coefficient sheaves. You're twisting the Galois action. And you can think of it as a kind of mild operation because it's not actually changing the underlying group. So it's more like these varieties are analogous to non-orientable manifolds, where if you want Poincare duality, you have to have an orientation sheaf, like you have to have some action of the fundamental group. But again, just to emphasize, like this is mild in some sense because it doesn't even change the group if L is not equal to P. If L were equal to P, this would be a completely different discussion, which we'll have a bit later. So if L equals P, then this object, which was conjectural for a long time and then constructed, is very different from ZL if n is not equal to 0. Okay, so now I've given you the flavor of this pairing. So this is the result of my PhD thesis. So we're going to assume P is not 2, right? P is not L, and we're interested in L equals 2. Then the theorem is that this Artin-Tate pairing is symplectic as Tate had conjectured. And the proof of this theorem is, I think, for me, it's exactly an instance of this metaphor. Because it's a statement about algebraic geometry and characteristic P, but the proof is borrowing key ideas from topology. But it's not just like the transcription of topology to algebraic geometry, but rather the proof gives new results in topology. So it characterizes exactly when the linking form on a manifold would be symplectic. And I'll just remark that it does generalize to higher dimensions. Like you don't have to talk about surfaces or 5 manifolds specifically, but because of simplicity and historical reasons, I'll just stick to that case for this talk. Well, both. So I could take a 2n dimensional variety over FP or a 4n plus 1 dimensional manifold. Okay, so I say that it has to do with topology, and let me just kind of sketch why. So one key traction comes from thingies called Steenrod operations. So these are natural transformations, square upper I, go from Hn to Hn plus I. And you can think of them as kind of like derived functors of Frobenius. Okay, so these cohomology mod 2 is an algebra over F2. So it has a Frobenius squaring operation. But the claim is that it's not just like any old algebra in characteristic 2, it arises by a more specific process, which equips it with extra structure. Let me give you some examples. So if you take square I and you apply it to Hi, you land in H2I. And in that case, it really is just the squaring operation. So let me show you an example of like kind of more novel operation. So We know that this cup product is commutative. So if you have two cycles, cocycles u and u prime, then their commutator, u prime minus u prime u, it's the boundary of something. Okay, so it becomes zero in cohomology. And Steenrod constructed a higher cup product, like a cup one, of which the boundary is this commutator. Now, if you imagine taking u to be equal to u prime, then the left side of that equation is zero for like really tautological reasons. So you're getting now this cup one of u tensor u is the thing whose boundary is zero. So it's a cocycle. So it defines a cohomology class. And that cohomology class is square I minus one, the kind of first derived functor applied to the class of u. That's an example of who the Steenrod operation is. Here are a few, well, how did the rest of the Steenrod operations go? Kind of by a similar inductive process. We discussed the cup one as a thing, boundary is the commutator of the usual cup product. And then the cup one has a kind of anti-symmetric nature. So there's like a cup two product whose boundary is the anti-commutator of the cup one product, and so on and so forth. There's a cup j product whose boundary is like the commutator or anti-commutator of the cup j minus one product. So that's what this sequence, you just get this sequence of like higher cup products. And when you specialize them to diagonal elements, elements of the form u tensor u, those are the Steenrod operations. That's why I'd say it's like a derived functor of Frobenius. Frobenius is a multiplication. It's a function of two variables. You specialize the variables to be equal. And here you have these like higher cup products. It's a function of two variables. You specialize the variables to be equal. Those are the Steenrod operations. So having said that, given a relatively hands-on or concrete handle on these things, I'm going to immediately turn around and mention like a kind of maybe less concrete interpretation. So there's another perspective on these things, which I mention now because they'll be useful a bit later, which comes from stable homotopy theory. And what is this about? So it begins by trying to take the collection of all cohomology theories on topological spaces and then just organize them into a category. It's called the category of spectra. Okay, so the objects will be like cohomology theories, the morphisms will be like natural transformations. And example is that just any ordinary abelian group like Z or Z mod P defines for you a spectrum. And these particular examples represent singular cohomology with Z or Z mod P coefficients. Now, kind of, you get more exotic examples. Spectra can always be represented by sequences of spaces. Not every sequence of spaces is a spectra, but an example that is the sphere spectrum is represented by sequences of spheres. Okay, so this is like a exotic cohomology theory. Now, spectra have notions of direct sum and tensor, which lets you define the notion of a commutative ring object, which allows you to do commutative algebra in this category. And well, you certainly have examples coming from the usual theory of commutative rings. So ordinary rings, such as Z or FP, define commutative ring spectra in this sense. But there are also exotic examples, like again, the sphere. The sphere has a commutative ring spectra structure, coming from the fact that when you smash together lower dimensional spheres, you get a higher dimensional sphere. So why do I mention this? Because so this actually makes the sphere into the initial commutative ring spectrum. So you have like maps of commutative rings from the sphere to Z to F2, let's say. So Z is longer initial in this category. And doing this, it buys you kind of ways to extend, like to see more endomorphisms. So the endomorphisms of F2 as an abelian group are small. You just have F2. But endomorphisms over this sphere, it's asking for like preservation of less structure, is big. It's in fact the Steenrod algebra, it's the thing generated by these square eyes. So in this perspective, because I just want to see another way to think about these Steenrod operations, namely that they arise as endomorphisms linear over the sphere. This thing? Oh, is it formal? No. Okay. Yeah. So Okay, this discussion seems to have gone off the deep end to some extent. Like what, talking about the size of Brauer groups. So what does this have to do with this pairing? The connection to the Arden-Tate pairing comes from a formula that you have a smooth proper surface over Fp, p not equal to 2. Then for all elements in the Brauer group, let's say 2 torsion elements, you have a identity between the self pairing of U and some sequence of Steenrod operations applied to U. Okay, suitably interpreted in top cohomology. And well, we're interested in the thing is symplectic. So we want to know, is the left side 0? Okay, so the point is we can rewrite it as the right side. Of course, it's not really clear why that's useful. So now we just need, in order to actually use this identity, we must have a way to calculate these Steenrod operations. And so here, it was somewhat fortunate that when I learned about the conjecture, I was simultaneously like reading a textbook on algebraic topology, and lo and behold, there was some inspiration in this textbook. So we're going to draw some inspiration from algebraic topology in order to calculate these kinds of Steenrod operations. And the point is that, at least in topology, you're talking about a 5-manifold, you could compute this square 2 square 1 operation in terms of what are called Stiefel-Whitney classes. And you could give an exact criterion for when the linking form would be symplectic. Now, it's not always true. So it turns out to be that the 5-manifold should have like a spin C structure. So in topology, the buck kind of stops there. But then, miraculously, in algebraic geometry, it turns out that the condition you write down is always satisfied. So there's kind of like something special about the position of the Stiefel-Whitney classes of algebraic varieties over finite fields. So I don't really have time to explain fully why, but let me give a heuristic. So when we discussed earlier what is the topology of varieties over finite fields, we gave maybe a more specific picture. We said a surface over a finite field looks like 5-manifold fibered over the circle whose fibers are complex surfaces. And so the Stiefel-Whitney classes of a complex surface are in some kind of special position. Particular complex surfaces are spin C, and Stiefel-Whitney classes of a circle are trivial. That's a very special position. And so that kind of explains why the Stiefel-Whitney classes of a surface over a finite field would be in special position. So it explains of S's Stiefel-Whitney classes, which makes the pairing always alternating, always symplectic. Any questions? Yeah, so what I'm using is that what I need is like some Stiefel-Whitney class or combination of such has an integral lift. And I will use the Chern classes to exhibit an integral lift. Okay, so this is still somewhat old news, 2020. But so I'm going to conclude the discussion of the like L not equal to P part of the conjecture there, and now proceed to discuss the L equals P part. So first of all, like what was the status? Well, what's known? So remember, Tate had conjectured that this Brauer group, its size is a perfect square always. Oh, the conclusion is that this case is somewhere back. That this pairing is symplectic when P is not 2, because we're talking about L equals 2, so P not equal to L. So we get this symplecticity. The proposition and the subsequent calculation, which is actually a bit longer, but this part is like maybe the most difficult part, but it's analogous to something which is kind of well-known in topology. It's easy in topology, difficult in algebraic geometry, at least it's true. So yeah, we have kind of two halves. One, relate the pairing to Steenrod operations, and then the second half is compute them in terms of characteristic classes. Okay. Further computation. Okay, so what happened with L equals P? So Tate conjecture to the size of the Brauer group is a perfect square for all primes at all L parts, including L equals P. But he didn't quite conjecture that the form is symplectic. when L equals P, because he actually didn't really define the form. And why didn't he define the form? Because he didn't even have a cohomology theory. So we discussed before, you can make this linking form if you have these sheaves, EP of n, and you have concrete duality, you can make a definition, but he didn't have the definition. And because he didn't have the sheaves, he didn't have concrete duality. That was the status in 1966. Now later, Milne resolved these problems. He defined the sheaves, he proved the concrete duality, he constructed the desired bilinear form, he showed it's skew symmetric. So I'm going to call that the Milne-Arden-Tate pairing. So really what I called before, the Arden-Tate pairing should have been some combination of what Arden-Tate did when L is not P and what Milne added on when L equals P. And these sheaves then do really become different. They become some kind of logarithmic differential forms. They're not just CP with some twisted action. Okay, so because of Milne's work, one can then formulate the question of whether or not this Milne-Arden-Tate pairing is symplectic. And it's skew symmetric, so it's really a question about what happens when P equals 2. P equals 2, the story is still unclear. So that's what I'm going to talk about. So I'm going to describe work in progress with Shachar Carmeli. And the expected theorem is that, in fact, it is symplectic, even in this most difficult case when P is 2. So kind of L equals 2 was like the major difficulty before. P equals L is another difficulty. And now we're talking about L equals P and L equals 2, so P equals 2. So this is where all your difficulties align. All these difficulties kind of collide and amalgamate. Okay, so, well, you could say, why don't we just do the same thing we did before? And indeed, the strategy begins the same way, but it quickly runs into significant difficulties. So I'll say something about one of these. So one subtlety which we didn't appreciate at the beginning is that there's actually like two flavors of Steenrod operations at play. There's like things called infinity Steenrod operations, which are kind of a topological nature, which I described before. And then there's something called motivic Steenrod operations. So I put a subscript M there. And those were constructed by Voevodsky, at least when L is not P, and then kind of extended by Franklin and Spitzwick to the case where L equals P. There's these two guys floating around. One of them we're already kind of familiar with. So the kinds of things we discussed previously were the infinity guys. The motivic ones, well, they don't have any analog in topology, or at least not any new analog. So they really are things that come from algebraic geometry. And you can kind of, one way to think about it is that, as I discussed, the infinity operations come from spheres, come from spectra, and make the spheres, build them out of spheres. The motivic ones come from motivic spheres. Like, we'll repeat that story with spectra, but with projective spaces instead of spheres. Of course, if you try to like take the topological space, complex projective space, you will get a sphere. So if you kind of take this motivic story and try to crush it down to topology, you won't find something new. And you might ask, like, why didn't we recognize these motivic guys before? And the answer is because when L is not P, they aren't really new either. Like, it's like in topology. So the Steenrod operations, the two flavors are essentially the same when L is not P, but and that's something which was kind of partially analyzed by Brosnan and Joshua, and then fully analyzed by Bach and Hopkins. But that breaks down significantly when L equals P. Then they're very different. And so this is something which we didn't like appreciate that enough at first, but it turns out that we really need both flavors of these Steenrod operations. So previously I described the strategy of proof in two steps. Like step one, calculate the pairing in terms of operations, and it turns out that's something that's really about the infinity operations. Step two is calculate operations in terms of characteristic classes. That turns out to be really about motivic things, and that part is difficult. So a lot of the work just to replicate that part when L equals P. And then you also need to connect the fact that you use two different operations in two steps. You need to reconcile that. So yeah, I guess the main problem is like these motivic operations, motivic Steenrod operations, they were recently constructed by Franklin and Spitzwick. In this case, we need them when L is P, but one doesn't really have a good handle on them. Like their structure remains largely mysterious. And sample questions which we would need to be able to answer to run the strategy include like, what's the coalgebra structure on this thing, this motivic Steenrod algebra. It should be a Hopf algebra, but conjecturally its coproduct is given by something called the Cartan formula. We don't know it, and we need it. How are the motivic and the infinity operations related on a given cohomology group? We need that. Are these motivic guys compatible with these wrong way Umkehr maps, push forward maps on cohomology? We need that kind of thing as well. And we don't really know any of these for the Franklin-Spitzwick operations. In fact, these kinds of things basically like long-standing features of Voevodsky dating back to the early 2000s. So basically our status was like we eventually figured out a roadmap of things that should be true that would lead to the conclusion, but they were bumping into like these long-standing open problems about the structure of motivic Steenrod algebra. We thought we're dead. There's no hope. So we need some kind of new approach to these motivic Steenrod operations in order to proceed. And it turned out that there was a miracle. There was a solution coming from new perspectives on p-adic cohomology theories, which were introduced in the works of Bott, Morrow, Schulze, Drinfeld, and Lurie, whose name I botched because he really helped us out a lot with this, like enough to be co-author, although he declined to be such, but okay. Okay, so what's going on here? So Bodmer and Schulze discovered some kind of universal p-adic cohomology theory or p-adic schemes. They call it prismatic cohomology because it kind of refracts into all the known cohomology theories, such as the crystalline or Durham or Étale theory. And we're going to use that. And why is it useful? A crucial aspect of it is that their theory works really well in mixed characteristic. So for example, I had discussed the difficulty of defining the sheaf ZP of n. And then Milne did it. Of course, one knew what they were in characteristic 0, but characteristic P, Milne found a way to define them as logarithmic directional forms. But Bodmer and Schulze defined them integrally for a scheme over ZP. And spec ZP is this thing which interpolates between characteristic 0 and characteristic P. And so it has a foot in both these worlds, like the L not equal P world, which we kind of understand, relatively speaking, and this kind of more mysterious and world where L equals P. Now, why is that actually useful? First, I'm going to digress briefly. So there's a kind of key philosophy underlying this, which is that the topology of spaces in characteristic 0 and in characteristic P become similar, very similar, after you add enough P power roots to make them perfectoid. So the examples are you take QP and you adjoin a full system of P power roots of unity and you complete. Then suddenly that looks very similar topologically to if you took this characteristic P field FP, Laurent series T, and adjoined a system of P power roots of T. So I think this is like another instance of our metaphor that like these two creatures, the characteristic P and the characteristic 0 world, which we know one of them is terrifying and the other is, well, relatively familiar, become similar from a certain angle. And this is a philosophy that underpins the theory of perfected spaces as initiated by Schulze. And I'm telling you this because we're going to want to use it. We're going to make our things perfectoid. We're going to take an integral version of this construction. We're going to take ZP and add to it the system of P power roots of unity. And it's an integral thing that interpolates between characteristic 0 and characteristic P. It's like a bridge. Okay, it has these 2 points. One on the near side, the familiar one, characteristic 0. We understand kind of the motivic Steenrod algebra there quite well, thanks to Voevodsky. And then on the far side of this bridge, you have this kind of seemingly intractable, more mysterious characteristic P world where we want to get. And what we're going to do is kind of use this bridge, use this theory to transport key structure from this characteristic P world, a characteristic 0 world where we understand things by way to this characteristic P world where we need it. Okay, so you may have noticed that I've like said almost nothing of content in the past few slides. I just drew some cartoons, made some metaphors. So let me, in the final part, just try and say, what is it that we do? Okay, in terms of what they did. So Bodmer and Schulze defined prismatic cohomology groups. And then Grunfeld and Bottleri explained how to construct a category, which is like a category of coefficients for prismatic cohomology, a category of prismatic DP modules. You can take coefficient. You can take prismatic cohomology with coefficients, an object of this category. What we do is to make a definition, some definition of prismatic cohomology with coefficients in the motivic sphere spectrum, and we make some definition of a category of modules over this motivic sphere spectrum, prismatic sphere, or we might call it a category of prismatic spectra for schemes of GP-SIC. Why do we do this? Because remember I had said the infinity Steenrod algebra, the topological thing is understood to be endomorphisms of FP over the sphere. And we're going to want to view or make our motivic Steenrod algebra as endomorphisms in this category we define of FP. Now, I'm starting to like lie a little bit where, okay, sometimes I say prismatic, I mean symptomic, sometimes I say motivic, I really mean motivic. But anyway, this is the picture. And using this perspective, we can and move enough information from this characteristic 0 side of the bridge to the characteristic P side of the bridge. Information in characteristic 0, which was established by Voevodsky, we can send over to characteristic P to get what we need. So in the spirit of Sam's earlier question, I just want to remind you, what is it called for? So it's for this like expected theorem that when you have a smooth proper surface over FP, for any P, including P is 2, then the Brouwer group has this natural symplectic structure, as was anticipated by Tate. So in that extremely vague talk title, this is the structure which I alluded to we're searching for. And I hope that I've convinced you that we've also encountered some interesting mathematical structure on the way. And now this is the end for real.
Question or comments? Anyone?
Your construction works for all prime in a uniform way, or you just for all the prime P, you just use Mina Argentita?
Are you talking about the construction of
Symplectic statement.
Of what?
Of the symplecticity statement of minus.
Oh, okay. So let me say the question I think was, is the construction of the pairing uniform? And well, that depends on what you interpret as uniform. So here's the sense in which it's uniform. You go to the definition. Sorry about this. Okay, here's the definition. Now, this definition is going to work no matter who L is. L equals P or L is not equal to P. The same is a uniform symbol which defines the pairing. However, the actual meaning of those symbols does depend on whether L is P or not. Like I said, when L is not P, then this basically, you can ignore these 2s and 1s. Well, when L equals P, it was like a serious effort to construct what this thing actually means. But in the end, you call it the same name.
Any other questions?
You explained early on that the corresponding theorem fails for number fields, fails over Z. And should we think that your picture with fibering over S1 kind of gives an explanation for the discrepancy between function fields and number fields here? Or?
Yeah, that's a good question. Yeah, so yeah, you could interpret it as like the topology of varieties over number fields doesn't have this special form. Number field, like the integers are like just some open 3 manifold. So that's a possible way to look at it. But I don't know of a way to interpret the pairing in extremely close terms to topology like I did here, where that becomes super clear. But one kind of funny remark is that, oops, we're gonna have to wait a while again. Okay. I'm just gonna make a remark. Whoop, I went in the wrong direction, I see. which doesn't really answer your question, but I think it's an amusing thing. So I had explained before that there is an earlier result of Liu, Lorenzini, and Reynaud, who showed actually it is always a perfect square, and they actually do it by choosing some curved vibration, make a birational transformation, compare the Brauer group to an actual Tate-Sharp-Average group, and the pairing to the pairing. And somehow the Pund-Stoll discrepancy, what they find is that the exact discrepancy for this to be true is the same as the difference between this and the Brauer. So there's a kind of strange numerical artifact that the discrepancy between what happens in geometry and arithmetic is, there is a small discrepancy there, and it's exactly the same as the failure of this thing to be true.
Thanks.
For the time reason, let's stop here and thank the speaker again.